let's see, the order, the kind of differential equation, whether it's one variable or more than one variable. So we classify that as ordinary versus partial differential equations. We talked about linearity. I think that was a tricky one. When a differential equation is a linear differential equation, because we'll have ways to solve for it if it is linear, and if it's not, then we'll need to find something else to do. And the types of solutions that we get could be an implicit or explicit solution, and we talked about implicit and explicit types of equations. So now let's talk about the parameters here. So solving differential equations, there's a process where we take an antiderivative or an indefinite integral. So we remember back in Calc 2, when we do that, we have a plus c. So if we do an integration and we get a plus c, then that c can be anything we want. Well, not anything we want, but anything anybody else wants. And so that is going to be a parameter. And if you have higher order differential equations, chances are you'll have more than one parameter. And so the number of parameters, the number of plus c's that you get when you integrate would be your number parameter type family of solutions. So one parameter family of solutions will have usually comes from a first order differential equation. Now, in Calc 2, when you guys did those, you had an acceleration, you found the velocity by integrating, you found the position by integrating again. So that entails this one, or in this case, two parameter family of solutions. And so usually, do you remember those problems where you're standing on top of a building and you throw a book, and then you have to find out the motion, the position, and then the gravity's negative 9.8 or something like that. And then sometimes they give you additional information, like you toss the book at a certain speed, like at 10 meters per second kind of speed. And so that allows you to solve for the arbitrary constant. Remember that? Should we try one of those problems? Nah, let's not. So anyways, if you're able to find those arbitrary constants, if you're able to solve for those arbitrary constants, then you're looking at a particular solution. And a particular solution usually comes from solving for a differential equation that has an added information. And added information would be the piece of information that helps you solve for the arbitrary constant. Now, sometimes the solution is obtained from a family cannot be found by assigning a value. And so that's called a singular solution. Okay. All right. So let's see if we can take some more. All right. This looks like a problem to look at. So for example, we have a differential equation that looks like this, and the solution is given by this, which is how many parameters? Is it one parameter, two parameter? What do you guys think? Should be two? It's a little tricky, but in this case, it's a one parameter family. I know there's two C's in there, but those C's are the same C's, so it's really just a one parameter family of curves that fits that particular differential equation. So this is a one parameter family of solutions. Um, and if we had some more information, we can actually solve for the arbitrary constant C. Like maybe it passes through a specific point. You want your solution to pass through a specific point. And so is there another solution to this differential equation is the question. Wait, do you guys understand this whole one parameter business? Don't think about how they got the answer. Just think about the answer itself, and then try to understand how the answer relates to the differential equation. So it's a one parameter because it's a first order differential equation, so we would just expect one arbitrary constant. You guys have seen one parameter stuff, right? When you integrate, there's a plus c, and then do you know how the graphs of these things look like? Let's see if we can graph it. So y is equal to 1 over 16 for c times x squared plus 4c squared plus x to the fourth. So when c is equal to 1, is it a parabola? Looks like a parabola, but it's technically not, right? A parabola has, it's a degree is 2. The degree of this polynomial is 4, so this is technically a quadric, not a quadratic, quadric. Anyways, the point is that if I change the value for c, I'll get a different curve. And so you change the value for c. And there's nobody saying anything about excluding negative numbers, so we can include negative numbers here also. So as your c changes, your graph will change. And then so if you imagine each of these curves as being a curve that represents a solution, that could be a possible solution to the differential equation. Now, for some reason, I actually want to go through the point 1, 1. Then I need one specific solution. So I would usually be able to solve for the value of c so that I can make my solution actually pass through that point 1, 1. And sometimes there's only one. Other times there might be more than one. That would make your solution kind of oops, pressing the wrong buttons. That would make your solution not so unique. So so those are the different families of solutions when we talk about parameters. So they're saying, they're asking here, is there another solution to this? Is there another solution to this differential equation? There's an easy one. What do you think it is? And when I say solutions to a differential equation, your answer should be y equals to, or whatever the function name is, f of x is equal to. In this case, y is the dependent variable, so y is equal to what is a solution to this differential equation? Any ideas? No? You guys know what I'm talking about? We are in differential equations, right? Okay. Y is equal to 0 would work, right? If I had y is equal to 0, then y prime is equal to 0, right? So if I put y here, y prime equals x times y to the 1/2 power. So y prime is 0 is equal to x times 0. 0 is equal to 0. So that works. Maybe I should also say that this, in fact, is a solution to this differential equation, because if I find out what y prime is and I put that into the differential equation, I should get a true statement, right? So what's a derivative of this? All right, let's practice taking the derivative. What's a derivative of the solution that I got here? 8cx. C is constant. Plus what? Is that right? We can. We'll see. Are you looking at simplifying this? So 1/4 2cx plus 2x cubed. What? Just x cubed? Can we also take out an x? So that's what? X squared. Plus 2c plus x squared. Okay. All right. So that's what the derivative is equal to. That would be the left-hand side. On the right-hand side, we were supposed to have x times y to the 1/2 power. I wonder what x times y to the 1/2 power is. So that's 1/16, 4cx squared plus 4c squared plus x to the 4th to the 1/2 power. See if we can simplify that. So the 16 to the 1/2 is 4, so that's 1/4. How are we going to take the square root of this thing? Any ideas? Can you take the square root of that thing? It's what? Complete the square? We have to do this off to the side? Let's see. How do you complete the square? You got x to the fourth. Hey, there's an x squared here, so why don't I put that first? 4c x squared plus 4c squared. So half of this and then square it. Isn't half of that and squared equal to this already? Well, that's already a perfect square, right? So this whole thing must equal to x squared plus the square root of 4c squared, that's 2c. Well, that's what this is. So the square root of that is just that itself. And so what do we have left? We have exactly what we have for the other one. So that matches. So that is, in fact, the solution to this particular differential equation. Okay. It's probably a little bit more time than I wanted to spend on this, but so what did we do here? What did we do? What is all this work that we just did? What? So all we did here is we verified the solution that in fact that y equals 2 is in fact the solution to the differential equation. You know how in algebra you solve for x, and then we don't do this anymore because we're all grown up, but we used to take our value for x and plug it back into the original equation to check if it's correct. So we're verifying the solution. That's exactly what we're doing here. And you're going to be doing for a little while before you start solving for your differential equations, but just verifying the solution. All right, let's move on. I don't know if we'll get to too much of this, but a system of differential equations is a list of two or more differential equations with, well, two or more functions that you're trying to solve for. And so I generally don't get to this topic in the class, but we'll see if we can try to get to that topic. It does require some linear algebra stuff that you may or may not know, but we'll see if we get to do any systems of differential equations. I will point out some examples when we come to doing examples. I think somewhere in chapter 3 they do some examples of systems, and we'll take a look at that. All right, what else? All right, that's where we should have ended last time. So now let's talk a little bit about the theory of some differential equations. So some theory about differential equations. The main topic is going to be called existence and uniqueness of the differential equation. But before that, we need to define a term that we're going to be using a lot, and that is an initial value problem. So in the beginning, we'll just talk about first order differential equations, and so we're just going to talk about first order initial value problems. But in general, an nth order initial value problem is an nth order differential equation that has some added conditions to it called initial conditions. And the initial conditions are a set of other equations or other, not parameters, but yeah, other equations, some other information that tells you a little something about the specific differential equation that you're solving for. So the whole setup might look a little confusing, but if we throw up an example over there, it should hopefully clarify things up a little bit. And let's use a Calc 2 example. Let's do that equations of motion. Like, let's pretend we have an acceleration of projectile. And let's say it's a of t equals negative 32 feet per second squared. And then you throw this off of a building. Let's say you throw it at an initial speed of, I don't know, 10 feet per second. And then initial position, let's say you're up on a building 20 feet high. You remember those problems back in Calc 2? Or maybe even in Calc 1? So this is an example of an initial value problem. It might not seem obvious that we're dealing with derivatives, but we are, and we should know that from Calc 2. If we let x of t equal the position, then we have a of t is equal to x double prime of t. So this is your differential equation. What order differential equation is this? The second order differential equation. Is it linear or nonlinear? Is it linear or nonlinear? Yeah. No. So it is linear. Why is it linear? Oh, you're going to say nonlinear also? I think it's linear because remember, nonlinear, it's nonlinear if any of the functions that you're solving for, in this case, we're solving for x of t. Any of the functions that we're solving for is being composed with another function. So in this equation, if I focus just on the x double prime equal to 32, that equation has the dependent variable x double prime, and it's not being squared, it's not being taken to the sine or ln of anything, so it's just by itself. And as long as it's by itself or being multiplied by another function, then it's going to be a linear function or linear differential equation. So this is a second order linear differential equation. Now, if we were to solve for this, we would integrate, right? And so we would integrate to get x prime of t equals negative 32t plus a constant. And I'll put C1 because I'm going to integrate again. Oh, before I solve for this, sorry. Before I solve for this, I should denote that this is a differential equation subject to the initial conditions that, so there's two pieces of other initial conditions in the problem. What are they? The what? Initial speed. How should I denote the speed? Yeah, so its initial speed is going to be 10 feet per second, but what do I want to call it, I guess, is what I'm asking. What? What? Yeah, but before I solve for this, before I get C1, x prime is 0. So that's the initial condition part. That's one initial condition. And then what's the other one? The initial position, which is what? X of 0. So you see how that matches up with the initial conditions that they have in the example? So we have a differential equation. We have a couple of initial conditions. And so we have what we would call an initial value problem. All right. So we're going through the solution to this initial value problem because we can, because we've done it before. But normally we just study this and then we would learn the techniques later. But this is easy enough to do. So if we were to integrate again, I could solve for C1 right here, but let's integrate again to show you that this solution, x of t, is a two-parameter family solution because we come up with two arbitrary constants. Now, the thing about the initial conditions is that it allows us to solve for those arbitrary constants. So we'll put the first arbitrary constant here. When x is equal to 0, x prime is equal to 10. So your x prime of t is equal to minus 32t plus 10. And then your x of 0, this is the actual solution, minus 16t squared plus 10t plus 20. So this is your solution to our first example of an initial value problem. Okay? Any questions? All right. So now that part's a definition part. Here's a theory part, existence and uniqueness theorem. And this could get a little complicated for us, but let's see if we can go through it. So usually when you're trying to solve for these differential equations, there's an implied interest in the domain of this. And so they talk about that in this theorem. So a rectangular region in the xy plane defined between a and b and x, and then for y's between c and d. Let's say it contains a point that we're looking for, x naught, y naught, in its interior. So if f of x, y, and the partial of f with respect to y are continuous on this rectangle, then there exists some interval I around x naught that's contained in AB, and the unique function y defined on this interval that is the solution of the initial value problem. Does that make sense? That's about as heavy math as you can get. All right, so what does that mean? Let's see if we can figure out what that means. That means if you have like a number line that you're dealing with, and then you have x naught on that number line, and then you're given the point y naught in that number line. So basically, if you have a differential equation, you want your solution to pass through this point x naught, y naught. And so what they do is they create a region around that point so that they can say that they're looking for a solution within that region. Okay, so we might not be concerned about all real numbers. Like in this example that we have with this projectile motion, we don't care about negative time usually. Like in this problem, we're not going to care about what happens when t is less than 0. So let's say our region is just going to be from 0 to infinity. Or we can just say it's from 0 to 15. So we might just be concerned about just a smaller interval than all the real numbers. So, and if we are concerned about that, then we're restricting the domain, then we're also probably going to be restricting the range. In this case, the y value range just goes from C to D. So it contains a point in the interior, and then if f of x, y, so this is going into some multivariable calculus that we won't worry too much about. And it's saying that the function here is continuous. So should we do this in a different color? Let's do this in. And I'll do something weird like that because it's possible that you have an implicit solution, which means if you vertical line test isn't going to work anymore. So let's just say some other weird things could happen where it might not be a function anymore, but you just have a regular relationship between x and y. But the function is smooth. There's no weird angles or weird cusps or anything like that. Yeah. You're only concerned about what's happening inside of the rectangular region. Oh, the loop? Yeah, the loop in this case, I don't think it matters whether it's inside or outside the rectangular region because you're going to do one more restriction and you're going to restrict this to a smaller interval. And so what they're saying here is now I'm going to move h units. Maybe it needs a smaller h. Oh, this is h. This is h. So from x naught, if I go h units to the left and h units to the right, that's what this is saying. X naught minus h to x naught plus h. So now I'm only restricting my curve to that, and this is the y of x that they're talking about, that now is an explicit function, is a function that we can define as a solution to this differential equation. Okay, and what they're saying here is that if you have a differential equation and some initial conditions, then one, you're guaranteed that you're going to get a solution. That's the existence part. And two, that's going to be the only solution. And that's the uniqueness part. So the word existence means you're guaranteed a solution on the given conditions here. And the uniqueness part means that is the only solution. That the solution is unique means there's no other solutions other than the one that you found. But sometimes we're concerned about if there's more than one solution. You can't see the red. It's red. Oh, whoa, 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 what happened? I need to shake things around. Wow, it is bright. Hopefully by the middle of the semester you guys can read my writing. I suppose I can just type it. There it goes. All right, where are we? Your Okay, so existence and uniqueness basically says that it exists and it's unique. So you can find a solution. Well, you might not be able to find it so easily, but there is one solution that exists. And I think most of the problems that you guys will run into for this section would be asking you to identify the interval where your solution would exist. And in our special case over here, the interval would actually be all real numbers, but for the sake of for the sake of the problem, if we put the problem in context as a projectile motion, then it's only going to be from 0 to whenever this projectile lands on the ground. And then so we can restrict our domain that way. Okay. All right. We'll try to not do so much of this, but there's also these things in differential equations called boundary value problems. And they're different from initial value problems because initial value problems give you a starting point and they have all the information at the starting point. Boundary value problems give you information about what's happening in the boundaries. So here there are actually two of them. So let me just take one out so it's not so confusing. So an example of a boundary problem would be this example where you have y double prime plus y is equal to 0. And then you have, instead of initial conditions, like instead of what happens at 0, what's y of 0 and y prime of 0, they tell you what happens at y of 0 or y of 1 and y of 5. So they're giving you information about the boundaries. And so it's called a boundary value problem. So the thing about boundary value problems is that there's no existence or uniqueness theorem for this. So you might be able to find a problem, or you might be able to find a solution. You might not be able to find a solution. So there's no guarantee that your solution would exist. Yeah. For this one, it could, but it actually might not give you a unique solution. Not necessarily, because I can have these two problems going from one y of 1 and y of 5 to be equal to 0. And then I could, like, if you look at a sine function that passes through those 2 points, and if you can either move it around or you can stretch it, it would still pass those 2 points, and then it's not guaranteed that. So if you find a solution, it might not be unique. So there's no guarantee of your solutions to exist, or if they exist, there's no guarantee that it's unique. It says in my notes we should try some problems. Let's see. Let's do one of them. Number 11. So we have a differential equation, y double prime minus y is equal to 0. And then it looks like we have a 2-parameter family of solutions. We got c1 e to the x plus c2 e to the negative x. So there's c1 and c2 have 2 arbitrary constants that they would have gotten if they tried to solve for this. And then they want us to find a solution of the second order IVP consisting of this differential equation and the given initial conditions. So this is our initial condition. So this already is a solution. Sometimes we would call this, it's a 2-parameter solution, but since we have not solved for the arbitrary constants, this is sometimes called a general solution. And we'll see later how they actually found this solution. But for now, let's just assume that somebody found a solution for us, and then And then we'll answer their question. We're given initial conditions down below. We have to make sure that our solution fits the initial condition. So let's see. How would you do this? Any ideas? We integrate y double prime? No. So let's say the integration's done. Somebody's already solved for this for us, and so we have the solution already. So we have a two-parameter family. We have a general solution. Now I want a specific solution that fits my initial conditions. Should we take a look at a graph first? Maybe a graph would help. I don't know. Did this graph help? So y equals, instead of C1 and C2, I'll say A times e to the x plus b times e to the negative x. And then I want to say A equals, I'll put a slider for now and maybe put actual values later, minus 3 to 3. And then B equals minus 3 to 3. Curve is shown outside. So depending on how we change the values for C1 and C2, I'm going to get different looking curves here, right? So those are my two-parameter family of curves. Now, I want at least the curve to pass by y of 0 is equal to 1. So if I were to consider that a point, what's the point here? X equals 0 and y equals 1, right? So I want to make sure that my point passes through 0, 1. So I can keep messing around with the different values here. Oh, it looks like that one passes through. But then if I change this value a little bit, I can still make this thing pass through somehow, right? So I know I can find a solution now. It's just my solution might not be unique if I only have one initial condition. So now I have a second initial condition that says y prime of 0 is equal to 2. Now, I don't know if I can draw that. How would I represent that? Let's see. How about a line passing through this point and has slope of 2? What's that equation of that line? 2x plus 1, shifted up 1. So I'm just going to use this as a guide to say that my, oops. Uh-oh. Did I lose my other graphs? Oh, that was all built up nicely and everything. All right. We have the point. Zero, 1. And then we have the line. I'm just going to use a line as a slope. So somehow I want to find values for C1 and C2. So not only does it pass through that point, but it also has the same slope. Does that look like it has the same slope? It's a little bit off. All right. Do you understand what we're trying to find? Graphically, do you see what's happening? Like two people nodding their heads. All right. Well, so I know that the function itself here, um, this is y. When I put 0 in there, I need to get 1, right? So y of 0 is equal to c1 e to the 0 plus c2 e to the negative 0 is equal to 1. So that's c1 plus c2 is equal to 1, right? Now, I also know that if I take the derivative of this function, that if I put 0 in for x there, I should get 2. So y prime of 0 is equal to c1 e to the 0 plus or minus c2 e to the negative 0 is equal to 2. So I have c1 minus c2 equals 2. Uh, Not quite. The wording is a little bit off, but we say that the solution here in the box, y equals that, is the solution to this differential equation. This is the original differential equation. It's a solution to that differential equation. And it happens to be a 2-parameter solution because it has 2 arbitrary variables. And also because it's a second-order differential equation. Okay? Now, so that's what they're saying in the beginning. And now what they want you to do is that given these initial conditions, that's what they're called, they want you to find a particular solution that is no longer a general solution. So they want you to find a particular solution that no longer has the arbitrary constants. So in short, they're really asking you to solve for the arbitrary constants. And that's what we are. That's where we are right here. We have 2 equations and 2 unknowns. We should be able to solve for this, right? So you got C1 plus C2 equals 1, C1 minus C2 equals 2. Anybody do this quickly? This is like 2C1 is equal to 3 if I add them. C1 is equal to 3 halves, and C2 is equal to negative a half. So those are my solutions. And in the end, I would say find a solution to the second order IVP, initial value problem, consisting of this differential equation and the given initial conditions. So my solution then is going to be y is equal to, instead of putting C1, I found C1, that's 3 halves e to the x plus, instead of C2, I found C2, that's negative a half e to the x. So that's my solution. Now in my graph, if I put those numbers in, the 3 halves for A and the negative 1 half for B, I should make it pass through that point and have the same slope. Let's see. A is equal to 3/2, 1.5, and B is equal to 1/2. That looks good, yeah? So remember, we're just using the green line as a guide to the slope. Let me see if I can make that lighter. But the actual solution is that purple line that we found, and it passes through that point. So let's take a picture of this and put it in our notes. This looks pretty cool. Let's be clear about what we have here. We have the solution to that equation. We have the point 0, 1, and then this is just a guide to our slope. Equals to 2. Okay? All right, any questions? Yes. You should. I'm not going to. And the idea is that if this is, in fact, if this was in fact a solution to the differential equation, you actually don't need to solve for C1 and C2. You could just take this C1 and C2 equation, the general solution, and plug that into the differential equation. So take the derivative twice and then subtract it from the original function. You should get it equal to 0 if it was in fact a solution. Okay, any questions? So you'll see problems like that. Let's see. I don't know if I want to do another problem. All right, here, let's take a look at this. Determine a region for which, on the xy plane, for which a given differential equation will have a unique solution. Let's do, I don't know, number 18. So determine a region in the xy plane. So this is going to dig back to the existence and uniqueness theorem, which in practice we won't be dealing with too much. But in terms of the theory, let's try to dig into the theory a little bit. And if you remember what the theorem says, it has something to do about your y to the n is equal to f of x, y, y prime, etc. That's like really confusing looking. In this particular problem, what's n equal to? What? N is equal to 1. This is just a first order differential equation, right? The dy dx is just y prime, 1 prime. So that's just y prime is equal to f of x, y. And then it stops at one less derivative than the order. So I'm just going to stop at the y. Which means f of xy is equal to the square root of xy. Now, back in pre-calculus, when you used to try to look for domains and ranges of functions, they want to know that they want to make sure that in the theorem, in the existence and uniqueness theorem, they want to make sure that this is defined for the rectangle that you're talking about. Now, usually back in pre-calculus, we worry about the domain if we have fractions or square roots, right? We can't have 0 in the denominator, and we can't have negatives in the square roots. So, question for you is, what x and y value combined is going to make the square root negative? If what? If one of them is positive and the other one is negative, then the square root is negative. So if x is bigger than 0 and y is less than 0, or if x is less than 0 and y is bigger than 0, then xy is going to be negative. So those are the bad places. And the good places is when, what? When they both have the same sign, they're both negative or they're both positive. So take a look at your xy plane. When is that good? So if you're in quadrant 1, they're both positive. This is okay. If you're in quadrant 3, they're both negative. This is okay, right? So the only thing here is that this is not okay. So it looks like you have two possible solutions. By the way, do we include the x and y axis? Is it okay to have 0 in the square root? Yeah, it's okay to have 0 in the square root. So if you're looking at this, then the axes would also be included. So let's see what the question was again. Determine a region in the xy plane for which the given differential equation would have a unique solution whose graph passes the point x naught, y naught. Did they say what x naught and y naught was? So if x naught and y naught were both positive, then you're going to be in the first quadrant. If x naught, y naught were both negative, then you'll be in the third quadrant. If x naught and y naught were different signs, then you're not going to have a solution for this. Okay? All right, so I guess the way to answer this question is that it's either in the first or third quadrants. Any questions? Boy, this is all theoretical and stuff. I was going to say we can move away from theory and then jump into some word problems. That's not very comforting. Let's just do some math. All right, well, we have to go through some word problems. So the next section talks about applications to this. And the sucky part about that is that we're going to start talking about applying this without solving for it yet. So we still don't know how to solve for a lot of these differential equations. And so we're just going to have to be patient and wait till next time. So let's go into the next section. So the big deal is that all these word problems will have some sort of rates rates of change, the change in this, something that tells you that the rate of change is involved. So the rate of change, whenever we hear that word, we should automatically think of the derivative, and that's not anything new. That's what we've been doing since Calc 1. The rate of change is the derivative. So what we're doing here is we're going to take a look at a problem. They say real life, but we'll put real life in quotes. A real life problem that's described in words, or to describe a particular scenario by saying the rate of change is something, then we're talking about translating that into a differential equation. And so this whole idea of doing a translation from words into our equations is called mathematical modeling. So the main thing to remember is that when you hear the word rate of change or rate, then that applies to derivative. So let's take a look at the simple example that you guys might have seen as in Calc 2. This is where they first say differential equation. The rate of change of a population is proportional to the population. Okay, so what we could do is what we generally do is we let the function that we're solving for equal to a specific variable. Now we can call that P for population, we can call it for Y because that's what we usually call our dependent variable, but we can call it whatever we want. Okay, so let A equal to the population. Actually, let's be more specific and define the independent variable as well. Let A of t equal to the population at time t. So now what you're saying is that I want to call my solution, the thing that I'm looking for, I want to call it A of t. Okay? So let's see if we can break up this sentence Hey, Jim. 2 minutes. The rate of change of the population is proportional to the population. So the is an equal sign. The rate of change of the population is what? What? The derivative. Call it dA dt or A prime of t. Proportional to the population again. So the population is A, and when we say proportional to that, what do we say? What? Variable. That's our differential equation. Now, of course, they're not all this easy to translate. And this is the easiest one, so everything else is just going to be more difficult. So I have 1 or 2 videos that help with 1 or 2 homework problems. There's a crazy homework problem about some floating thing. And so I think I have a video for that. I might share that with you guys. But I hope you guys are working on the homework assignments already because they're going to be due sometime soon. I think September 2 is the first one. So make sure you don't wait till the last minute to do that. All right. See you guys next time.